I know somebody at Apple in California, at Apple company, and he said, Dr. Rose, without your invention, the iPhone would not have the performance it has nowadays.
The properties of matter, the properties of materials, which are later on used for technology, they are decided in the microstructure. And in the end, it's the interaction of atoms with each other which are responsible for the properties. So when I think our era, the last 20, 30 years, are characterized by going into the small and smallest dimensions in order to tailor materials.
The collaboration between Harald Rosa, Maximilian Haidar and Knut Orban started in earnest in the mid-1980s.
There was a conference in Austria and Salzburg, which we three, Harald Rosa, Knut Orban and myself, attended. And we listened to the talks, and there was one presentation by the Max Planck Institute of Stuttgart where they presented a new microscope they are just purchasing and should be installed in the near future, which is 1.2 MeV microscope going down to, with resolution downwards to about 1 angstrom. But of course it's a unique instrument and it's very expensive. And Harald Rosa started to complain, just with a fraction of the cost of such a microscope, we could start a project to use a modern microscope, medium voltage microscope with 200 kilovolt, for example, and to compensate the spherical aberration and to have about at least the same resolution with lower energy, which means also able to investigate beam-sensitive materials.
Harald Rosa proposed in the late 1980s a novel lens design, the Rose corrector, also known as the hexapole corrector, enabling aberration correction in transmission electron microscopy.
I knew the principles. I always was good in mathematics, but without having a physical insight, I never could use the mathematics. If you have to understand that's the problem, and then you know how to go on to make approximations so that you get the result to a few percent, not exactly, but that you can show it will work and how the principle is, and then you can do it in the final design.
Maximilian Haidar realized Harald Rosa's idea and designed the hexapole corrector.
What you see here is just a magnetic hexapole element where the electrons then just at the center, which are passing by here in this hole, passing by, and they are reacting due to the hexapole field. And it means that a round electron bundle would be disturbed by a threefold astigmatism. That means we don't have a round bundle anymore, we have then a threefold shape of this electron bundle. And the important point is that one really could see single atoms or interfaces at different devices or different objects. That was really just a breakthrough, and that was actually, I would call it, revolutionary.
Knut Orban, together with Max Haidar, implemented the first aberration-corrected conventional transmission electron microscope.
The magnification which you can get in this way is up to about 1 million times. Now we have a development towards life science applications of this. It means the most exciting development in the moment is for me that biologists start to use such aberration-corrected instruments in order to advance resolution in molecules. Molecular biology nowadays is close to atomic resolution, but not fully. That means you can, in a molecule, which normally has 10,000s of atoms, you cannot resolve the critical atom.
Andrei Krivanek realized the first quadruple octopole aberration-corrected scanning transmission electron microscope with sub-angstrom resolution.
Essentially, we want to make every single electron that goes through the microscope produce some useful signal. And we can do that nowadays. And so we want to capture the electron, we want to tag its energy, we want to collect a whole bunch of them, and we want to process the images in innovative ways so you can pick up signals that the raw imaging would not give you. Mathematical processing can find out all kinds of signals. Still, it's important to have good optics, so that's where the correctors come in. Our type of microscope makes a tiny little probe and scans it around on the sample. And the probe itself, where it's focused, is actually like typically half the size of an atom, sometimes even smaller than that. To produce the tiny little probe, we can't use round magnetic lenses because they have unavoidable aberrations. This is something that's been known since 1936, and the solutions were proposed in 1948 by a very smart German professor, Otto Scherzer. That's kind of like one of the fathers of this field. And we simply follow one of his recipes. People had been trying for 50 years before it actually worked. So it got a little bit complicated, but if you do it right, it can be made to work. And that's kind of the big advance in microscopy, working aberration correctors.